This energy applications of nanotechnology works because materials are controlled at dimensions under 100 nanometers. The clever bit here is operating below viral scales. Dr. Wade Adams from Rice University identified global energy supply as humanity's most pressing problem over the next 50 years. As global energy demand continues to grow, developing efficient and sustainable generation and storage technologies becomes increasingly critical. For scale reference, a single biological virus particle measures approximately 100 nanometers across its outer diameter. Engineering physical materials at this precise subviral scale fundamentally transforms how devices convert electricity, manage thermal dissipation, and store energy across advanced industrial applications. Engineers and commercial manufacturers have already begun incorporating these specialized submicroscopic components into consumer products to achieve immediate measurable performance gains. However, early engineering development encountered a distinct setback when attempting to translate laboratory nanoscale synthesis into reliable large-scale commercial energy applications. Designers initially operated under the failed assumption that simply manufacturing particles under 100 nanometers would automatically yield consistent, high-efficiency electrical performance across devices. In initial physical testing, uncontrolled microscopic variations across subviral particle batches caused unpredictable energy transfer rates and severe performance inconsistencies in early prototypes. Without strict geometric control at sub-100 nanometer dimensions, early energy storage prototypes suffered from uneven active surfaces and unexpected thermal buildup during rapid charge cycles. This practical limitation demonstrated that raw material miniaturization alone was insufficient unless particle size distribution and surface boundary interfaces were strictly regulated. Engineers recognized that resolving this performance bottleneck required dedicated capital investment in research and development to establish precise, repeatable fabrication techniques. To resolve this setback, researchers developed advanced synthesis methods that enforced rigorous dimensional boundary controls, ensuring that all nanoparticles measured strictly under 100 nanometers. By standardizing nanoparticle size distribution relative to the physical benchmark of a single virus particle, material stability and electronic properties became highly predictable. This controlled structural uniformity eliminated unexpected thermal fluctuations, allowing consumer products to safely achieve increased electrical storage capacity and optimized energy conversion. Targeted capital investment from academic and industrial partners enabled the construction of specialized fabrication environments designed for producing uniform subviral energy components.
With production consistency fully demonstrated, engineers confirmed that nanoscale materials could deliver repeatable, long-term efficiency enhancements across commercial power systems. Having successfully resolved the particle stability limitation, researchers were fully prepared to deploy controlled nanostructures against major global energy challenges. The bigger problem was how to satisfy rapidly surging world energy demand over coming decades, while simultaneously decreasing environmental pollution resulting from energy use. Dr. Wade Adams from Rice University emphasized that solving humanity's long-term energy needs represents our single most urgent scientific priority over the next 50 years. Conventional energy generation and storage systems, relying on macroscopic bulk materials, appeared physically incapable of meeting escalating global demand without generating severe pollution. Traditional battery systems suffered from strict physical volumetric limits, requiring impractically heavy and bulky battery designs to achieve even minor increases in electrical storage capacity. At the same time, traditional lighting and heating devices wasted substantial portions of input electricity as uncaptured heat, driving up total energy generation requirements worldwide. Achieving dramatically higher power efficiency while curbing environmental pollution seemed nearly impossible until nanotechnology provided a radical methodology operating at subviral scales. The core engineering methodology strictly defines nanotechnology as any technical application featuring physical particles with at least one dimension under 100 nanometers. To visualize this submicroscopic regime, a single biological virus particle measures roughly 100 nanometers wide, marking the precise threshold where quantum and surface effects dominate. By structuring optical components at these subviral scales, engineered devices achieve a proven increased efficiency of lighting by dramatically reducing non-radiative energy losses. In thermal applications, sub-100 nanometer material architecture delivers a marked increased efficiency of heating, minimizing uncaptured thermal resistance across heating elements. For electrical energy storage, sub-100 nanometer structural design yields a significantly increased electrical storage capacity within surprisingly compact physical battery cells. This increased electrical storage capacity occurs because subviral nanoparticles vastly expand available active surface area per unit volume inside chemical storage architectures. As a direct consequence of these combined engineering enhancements, energy devices deliver a significant decrease in the amount of pollution resulting from everyday energy use. Reducing total fuel consumption through higher operational efficiency directly curbs harmful atmospheric emissions across industrial power plants and residential consumer electronics.
Engineers have successfully translated these nanoscale principles into commercially viable consumer products, elevating real-world efficiency in modern lighting, heating, and power storage. Because of these broad environmental and operational benefits, allocating capital investment into the research and development of nanotechnology has become a top priority. Academic centers like Rice University, alongside global engineering partners, continue directing research capital towards pioneering sub-100 nanometer energy generation and storage materials. Explaining these core mechanisms at a documentary level demonstrates how subviral scale structural manipulation provides practical answers to humanity's most pressing energy demands. Preserving operating limitations stated in original scientific literature ensures that nanoparticle synthesis and integration remain safely controlled during consumer product manufacturing. This evidence-based engineering approach proves that nanotechnology offers the essential technical foundation required to secure sustainable energy generation for future generations. Ultimately, controlling material architecture at dimensions under 100 nanometers provides the fundamental mechanism required to maximize energy storage and operational efficiency. From increased lighting and heating efficiency to expanded storage capacity and reduced pollution, subviral nanoscale engineering transforms modern power generation and conservation. Sustained capital investment in nanoscale research and development guarantees that sustainable energy systems will continue evolving to meet humanity's long-term power demands. Mastering physical mechanics below the 100 nanometer scale of a virus particle resolves the central challenge of modern energy applications through precise nanoscale engineering.